Next is Stokes Law. Now what is Stokes Law? Consider a viscous medium which is at stationary position, that is, which is at rest. Now let us say there is a small spherical body which is moving in this direction in this viscous medium. Now what will happen? The particles or the particles of the layers which are in contact with this spherical body will be dragged down or will be dragged in the direction of motion of this body. But those particles or those layers which are away from this spherical body will continue to be at rest position. So what is happening? There is this layer which is in contact with the spherical body. This starts moving in the direction of the movement of the spherical body, whereas the layer which is farther away from the moving layer, they are still at rest, right? So there becomes a relative motion between the layers of the viscous medium, due to which viscosity will come into play and it will oppose the motion. So what happens? A viscous drag force comes into play. Viscous drag force means an opposing force which tries to stop or oppose this motion. So this viscous drag force comes into play, which opposes the relative motion between the layers of the viscous medium, and it stops or it tends to stop the motion of that spherical body. So this viscous drag force is also going to increase with the increase in the speed of this body. Stokes found out that this viscous drag force or the opposing force which is acting on the body, on the spherical body, due to the relative motion between the layers of the viscous medium, this thing has this formula, 6 pi eta RV. This is the formula for viscous drag force. Now we can experimentally find out the value of this. Suppose the spherical body has radius r which is moving with velocity v. This medium has this density, the viscosity this, right? So according to Stokes, the force is proportional to what? Viscosity. The factors, I am writing the factors. Viscosity, it is proportional to radius and it is proportional to velocity, right? So what do we do in dimensional analysis? Let force be proportional to viscosity raised to power a, radius power b and velocity power c. Combining these factors, I'll get force is proportional to this b, c, or F is equal to k times, right? So according to dimensional analysis formula, the dimension on both LHS and RHS should be equal. What was the dimensional formula here? F. This is MLT minus 2. This will be equal to dimensional formula of right hand side. K is dimensionless because this is a constant which is used to equalize the left hand side and right hand side. Here I have M L minus 1 T minus 1 raised to power a, radius is length, and velocity LT minus 1 raised to power c. I'll get M raised to power a, L raised to power minus a plus b plus c, and T raised to power minus a here and minus c here. This is equal to M. This is equal to M L T minus 2. So equating powers on both sides, I'll get a is equal to 1, right? Now from t raised to power minus 2, t raised to power minus a minus c is equal to minus 2. So this all become positive. A is already 1, so c becomes 2 minus 1, that is 1. C comes out to be 1. Putting the value of a and c in this, L raised to power 1 here, so 1 is equal to minus a plus b plus c. A is 1 plus b, c is also 1, so they cancel out, so this gives you b is also equal to 1. Therefore putting value of a, b, c in this equation, I'll get F is equal to k, viscosity, radius and velocity, and experimentally the value of k is found out to be 6 pi. So the formula becomes 6 pi eta RV. This is the formula for force or viscous drag force which opposes the relative motion between the layers of fluid when there is a spherical body which is moving in a viscous medium with velocity v.